So today we're going to elaborate on what we started this unit on, which were gravitational forces, right? We started this unit talking about orbits and what orbital motion actually is, and what when astronauts appear weightless, what that actually means. And then we kind of generalized and just talked about small scale circular motion, but we want to go back to where we started. And why at the end? Because when we add Newton's law of universal gravitation, it gets a little more complex, all right? So we wanted to save this till the end. This is the last part of our circular motion unit. So we'll test over this early next week. We'll review and test over it next week. And then we'll jump into my favorite unit after that for pre-AP physics, which is work and energy. So that should be exciting. But for now, let's talk about Newton's law of universal gravitation. Now, up until this point, we know that, you got a star and you got a planet. That planet feels a gravitational force towards the star. And we are going to ignore the circular motion part of this for just a little bit. But we still have that. Like, pretend this planet is in orbit around the star. And so its velocity at that point, let's say it's moving clockwise, so its velocity at that point would be down. But what I want us to do is to hone in on that gravitational force and dig into it a little bit. And before I do that, I just want to remind you, well, this guy feels the same force, but in the opposite direction, right? Newton's third law. But because the mass of this guy is so much greater than the mass of that guy, this guy's motion doesn't get affected much, so we don't worry about it. All right. Now, you might have heard of a guy named Newton. Isaac Newton. You might have heard of Isaac Newton.
I know a little more.
Okay.
With his content.
So,
Physics.
So Isaac Newton was sitting under a tree one day, and what fell on his head?
A banana.
An apple. Next one, I'm throwing a marker at you.
I'll catch it.
An apple fell on his head, and then he stood up and he said, "Oh my gosh, I discovered gravity. Things fall down when we drop them."
Right.
That was his discovery, and now he's super famous for making that. That sounds silly, doesn't it? Yeah, because it is silly. Because when they say Newton discovered gravity by an apple falling on his head, that's a myth. That's just something to get kids interested or something. I don't know. Do you think that, Newton was around the 1600s. Do you think that before the 1600s, people didn't know that when you let go of something, it would fall down? I'm pretty sure you learned that early on in life. So when they say Newton discovered gravity, he didn't discover the effect of gravity. He mathematically explained gravity. That was the discovery, okay? And so that's what we're going to go over today, what Newton actually did to make that discovery. And so the first step, I'm going to erase this. The first step is understanding the following situation. Let's say I have a 5 kilogram sphere and a 10 kilogram sphere. Which sphere has more mass? I'm just kidding. Let's say that the 5 kilogram sphere feels a certain gravitational force. The 10 kilogram sphere, does it feel a larger? Sorry. Let me ask. I asked it that way first period and it didn't work out well. What can I say about, and we're not doing circular motion now. These things are just falling straight down. What can I say about the accelerations of these two objects? They're the same. And the ancient Greeks didn't think that was true because the ancient Greeks took a piece of paper and an expo marker and they dropped them and they realized the expo marker fell faster than the piece of paper. Well, this guy is heavier than this, so obviously this guy falls faster than that. Heavier objects fall faster than lighter objects. That was their physics law, right? And it wasn't true because Galileo figured out, no, if you just crumple that up, oh, now they fall at the same rate. So I've changed the amount of air resistance acting on it, right? And if you eliminate air resistance completely, a bowling ball and a feather will fall at the same speed. If there's no air resistance, they'll fall at the same speed because they'll have the same acceleration. Now, think about this question in the context of Newton's second law, which says the net force equals mass times acceleration. That net force is the gravitational force, right? In this case, we're ignoring air resistance. In the context of this equation, does the 10 kilogram object feel a larger or smaller gravitational force, or equal, than the 5 kilogram mass. So Stan says larger, other people are saying smaller. If they both had the same force, we know they have to have the same acceleration. What implication does that bring with it? If the force of gravity on both is the same, and they both have the same acceleration, then they would have to have the same mass. Right? So they can't be equal. You see that? You want to see that? That's knowing physics. That's seeing that in the equation. Right? Physics is all about equations and what they mean and what happens to one thing if you change the other. What do I know about the mass if the force and the acceleration on these two objects, well, they have to have the same mass. That doesn't make sense, though. So that tells me that the larger object actually has a larger gravitational force. Think of y equals mx, right? This is like y. What's the constant here? The acceleration. So that's like the m over there. And this m is like the thing that varies. This guy doesn't change in y equals mx. So if you make x bigger, y gets bigger. And if you go to the right on the x-axis, you go bigger on the y-axis. So the same thing here. If I know the acceleration of both these objects is the same, right? We know this stuff with math, with y's and x's. Here, y's and x's mean something. So we can talk about how that's reflected in reality. So we can say, if this guy's the same, if I have a larger mass, I get a larger gravitational force. The reason that people like to say the same there is because you've been taught that they have the same acceleration, and that is true. But because one has a larger mass, it must have that same acceleration due to having a larger force on it. Okay, and it scales like that, right? If you have twice the mass, it feels twice the gravitational force, which is why it has the same acceleration. Okay. All right, so that was the first thing. So Newton, what I'm getting at here is Newton's derivation or his discovery of the law of universal gravitation, which is Newton discovering gravity. So Newton determined, or he surmised, he observed, to explain what we just talked about here, the gravitational force has to be proportional, so I use that funky symbol, to the mass of the apple that fell on his head. You guys have heard of the addition symbol, right? And the subtraction symbol. And little kids' version of the multiplication symbol. Yeah. Little kids' version of the division symbol. Mm-hmm. The equal sign, I'm fond of the equal sign. The is defined as sign, I like that one. This is just another one of those, is proportional to. It's just another one of those. Right, so add it to your list. And there's a lot more of these. If you're going to be a mathematician, you ever learn set theory? Which I looked at like the introduction to set theory and decided I will never. There's a lot more. There's a lot more symbols. Set theory is what? Set theory's kind of weird. It's weird. I looked at some of it. It's very weird. Yeah, it's like based on how it's very abstract. That's why I say mathematicians are the smartest people, because what they do is so abstract that I just can't even begin to contemplate what it is they're doing. Yeah, it's crazy. So this just means it's proportional. You guys know what it looks like if y is proportional to x in an equation? It looks like this, right? Mm-hmm. Y directly proportional to x. If x goes up, y goes up. If x goes down, y goes down. So this just means as mass goes up, the gravitational force goes up. Now, Newton was pretty smart, and he thought, I bet the Earth has something to do with this too, right? I mean, no one had proved it yet, but he was like, I bet the Earth. The Earth has mass, right? All these, the stuff that we make from stuff that we take from the Earth. So the Earth has to have mass, and it has a lot of mass. And making some observations that we're not going to go into because I think I forgot about them. But I can tell you this. What Newton figured out next was that not only is this true, but the force of gravity is actually proportional not just to the mass of one of the objects involved, like this 10 kilogram mass, not just proportional to the other mass involved, the mass of the Earth, but is proportional to the product of the two masses involved. So I'll just say m1 times m2. So this was just a discovery that Newton made based on observation. The force of gravity. Now I'm talking about the force of gravity between any two objects in the universe. Okay, will be proportional to the product of their masses. Guess what? Anything that you can see, you are exerting a gravitational force on. And that thing that you're looking at is exerting a gravitational force on you. Yes, that means Fluffy. God rest her soul. Just kidding. Fluffy here. Fluffy is exerting a gravitational force on every one of you. And you're exerting one on Fluffy. I'm just kidding. This is synthetic. This is a joke. This is synthetic. You're also exerting a force on my, let's use my mouse. The mouse here. You're exerting that video, there's, yeah, whatever. The mouse there, you're exerting, you're exerting a gravitational force on the mouse. Why is it not accelerating towards you? Gravitational force of the Earth is pointing down. Stands is pulling it that way. There's two different dimensions, though they don't interfere with each other. They don't affect each other.
It's because the force is so little.
Say again?
It's because it's so little.
That is part of it. It's very low. The gravitational force, as for reasons we'll learn about today, is insanely small. Like your gravitational force on this thing is like immeasurably small. Almost. So yes, that's part of it. But it's still there. So given enough time, if that was the only force pulling on it in the direction this way, then it would accelerate towards you.
It would hit my face.
Yes.
At a very slow rate.
At a very slow speed. And I'll tell you this, if we go to outer space and do this, and just put stands there and put the mouse here, and then just isolate them for a while and watch, eventually, it's going to take a long time, but eventually that mouse and stands are going to come together.
I can do it right now.
No! What's preventing it, guys? Come on, think about it. What's preventing it? There is a force. It wants to accelerate.
What about friction?
Friction! Yeah.
Let's go, Evan.
The mouse wants to move this way. Well, what's preventing it? It's the friction that way. Right? That's why I'm not moving. That's why I'm not accelerating towards all the things that are pulling on me with their gravity. What I will do is accelerate towards the Earth if I jump off something, because its gravity is a lot bigger. Because I don't know if you've noticed, but the Earth is quite a bit larger than most of the objects that you come into contact with in your day-to-day life. Yeah, it's
Just a little bit.
it's significantly larger. Yeah. Okay, but maybe just a little. Okay. So Newton figured out that the gravitational force between two objects, has to be two objects, is directly proportional to the product of their masses. He also discovered that the force of gravity between the same two objects is inversely proportional to not the distance separating them, but the distance squared. So the distance separating them squared. So I'm going to modify this diagram over here. I'm going to pretend that these are two stars. So say we got, let's say a black hole and a star, right? Which we'll just call M1 and M2. And this distance is not the distance separating the surfaces of the two objects. Now, if we're talking the distance between actual stars, yeah, the stars are point objects. When you compare their sizes to the distances between them, right? You essentially just say, well, the distance between them is, yeah. But if we got two objects that are kind of close, like a black hole with a star orbiting close to it, which happens sometimes, then we measure the distances from their centers. That's the distance. And just so you know, because some students are like, well, what if you're like right here? Right? What if you're right next to it? It's kind of weird. Let's say you're in orbit. You're in the ISS. You're in orbit. You're like right on top, just like 150 miles up, right? Not very far in relation to the radius of the Earth. You're not very high up at all. And you're orbiting low Earth orbit. And then, who does it? N comes along, and she takes the Earth, and she's just like, and she just squishes the Earth. Because you can make the Earth a black hole. Did you know that?
Yeah.
We could turn the Earth into a black hole. We'd have to squish it. You can turn any object into a black hole. You just have to make it small enough. Okay? You just have to take all the mass and concentrate it into a small enough space so that the gravity is acting on every part of that much stronger because you get closer and closer. It turns out that if you made the Earth a black hole, first of all, what's the diameter of the Earth after you've squished it far enough to make it a black hole?
Not much.
What's the critical diameter? It's about 1.5 centimeters. So if you want black holes exist, by the way. So think about that. Like, this stuff happens. Stuff like this happens.
The Earth is flat.
Well, some people think that black holes are balloons. If you would like, I can definitely, if time permits, not today, but later, I can show you the evidence for black holes. I can show you the images that we have, because it was just last year or the year before that we took the first actual visual images of a black hole. Well, no, it was feeding. It was actively feeding. That's the only way you can see them, because guess what? If it's not feeding, you can't see a black hole, because you know what? It's a black background. Yeah. So it turns out, though, you take the Earth, you make it a black hole, you compress it from, 12,000 miles in diameter to a less than an inch in diameter, and it becomes a black hole, a very tiny black hole. But it still has the mass of the Earth. And the satellite that was just a little bit off of the surface of the Earth doesn't even care. It keeps orbiting it as if nothing happened. Okay? It lost the really pretty view. But now it's orbiting. It doesn't get sucked in. Black holes aren't magic vacuum cleaners. They're just astronomical objects like any other one. They just happen to have essentially punched a hole in space-time, and weird things happen. Weird things happen at the singularity of the black hole and at the event horizon, near the event horizon. But away from it, it acts just like a star or a planet or a moon. It's not much. You think this is funny? This isn't funny.
You look so detailed, oh my god, black holes, and you're pointing to a board like you're crazy.
You're crazy. I'm not crazy. You're the one that's crazy. All I wanted was a Pepsi. Just one Pepsi. And you wouldn't give it to me. Pop culture reference for the day.
I remember you saying something about in black holes, a space and time become opposite or something
Yeah.
like that.
Yeah.
It's just too much.
Yeah, we're not. Yeah, that's way beyond the scope of this class. Okay. Now, turns out that when you see these proportional relationships in nature and you want to describe them mathematically, just proportions aren't enough, right? And a good example of this I brought up before, Pivner. Right, bunch of experiments that told early chemists that if I keep the number of moles and the temperature constant, then the pressure and the volume are inversely proportional. If I keep the volume and the number of moles constant, then the pressure and the temperature are directly proportional. If I keep the pressure and volume constant, then the number of moles and these are all the individual gas laws, right? Charles' law, Boyle's law, and all that. That's the ones that take this and then condense it down into something more simplistic. However, when you do that, you got to hold two of the other things constant. But the equation doesn't make sense without the inclusion of what? That had to be experimentally determined.
This is why I think chemistry.
I almost failed chemistry.
And I imagine that that's a large part of the reason why we're so behind at this point. Because the assignments that we do in this class, we take longer than we probably should. The labs we take longer than we probably should. So let's try to up our game a little bit. Let's all try to up our game, be a little more efficient. This is the ideal gas constant.
Oh yeah, that changes.
This is it doesn't change.
Wait, no, the end changes.
The end all four of those things can change.
Yeah,
But the ideal gas constant doesn't change. That's why they call it a constant. No, shh, guys, you're missing the whole point. You guys, you're missing the whole point. You're focusing on. I'm trying to illustrate an important point right now. You're focusing on not the important points. Without that, this doesn't make sense. Yes, you can talk about proportions. You can write proportions like this, but you don't have an actual equation. What is so freaking funny? Dude, are you okay? Do you need to go sit in the pod? Calm down, dude. Calm down. So you need that proportionality constant. Not all physical laws require one. Newton's second law does not. There's no proportionality constant. It's just force, mass, and acceleration. This one does. This one does need a proportionality constant. And Newton called that proportionality constant big G. He didn't call it big G. He called it the universal gravitational constant. The universal gravitational constant. Little g applies at specific locations in the universe, right? I want to know the acceleration due to gravity at the surface of the Earth. Little g is 9.8. Somewhere else, the moon, 1.6. Somewhere else, the sun, like 30 or something like that. I don't know. So big G, by the way, don't confuse big G and little g. It's not like big G is like a bigger version of little g. They're two totally different things. Two completely different things. So don't make that mistake. The thing about big G is that Newton knew it had to be a thing. And he knew that when he combined these three, right, the proportionality constant and these two proportions, you get what is called Newton's law of universal gravitation, which I'm not going to write all out because I'll take the rest of the period. But it's Newton's law of universal gravitation, which in algebraic form looks like this. The force of gravity between any two objects is equal to the proportionality constant big G times the product of the masses of the two objects involved divided by the distance separating their centers squared. That is Newton's law of universal gravitation. Big G is not measured in meters per second squared like little g. Big G is the same number no matter where you are in the universe as far as we know. It doesn't change, so it is a constant, a universal constant like R in Pivnert. Yeah. And Newton, in the 1600s, right? He was about 20 when he did this, like he did everything else. Moritz, are you okay? Dude, breathe. If you need to have a moment, you can go. I'm sorry, I'm making it worse, aren't I? I just made that 10 times worse. Huh?
Has anyone here seen the Joker?
Yes.
Do you need a moment too, Carolyn?
I think so. I heard someone laughing gas.
Do I need to call down? Do I need to call the drug dog down? Do I need to? Yes.
Joker medal?
So those are they like, they're uppercase, right? Like,
It doesn't matter.
doesn't matter?
Usually they're lowercase.
Okay.
They're just masses.
The only one that really matters is G. Like, uppercase G and lowercase.
Yes. It doesn't matter what these guys are. Big G is a constant, always big G. Yeah. Now the interesting thing is Newton could do a lot of calculations without knowing what big G was. There were certain things that you could do regarding ratios. Anytime you could cancel big G out of a problem, you could do it. And then, so he could do some calculations with that, but he couldn't figure out what G was, what big G was. He knew it was a thing. He knew the equation didn't work without some proportionality constant there. He knew it had to be there, but he couldn't figure out what it was, because to figure out what it was required a very sophisticated, very sensitive experiment. So Newton came up with this in the late 1600s, mid to late 1600s, and it wasn't until the late 1800s that a guy first figured out what the value of big G was. So it's 200 years almost 200 years. I think it was maybe even over 200 years between the discovery of this law. And again, this is the apple falling on his head. This is really the algebraic distillation of what they're talking about when they say Newton discovered gravity. He discovered this relationship between the gravitational force between two objects that's separated by some distance. Carolyn, do you need to go? So, oh my gosh, guys. You're all fired. You're
paying us.
So?
I wish I was saying things.
Okay.
Stayed in college for this.
Okay. So I want to talk about G, because 200 years later it was discovered, and I have seen this person mentioned on a few previous CBAs, so it might be a CBA question. I like talking about this discovery because it's a very interesting scientist, historical scientist, that I think merits some discussion, especially since he made a whole lot of discoveries that are credited to other people. Some of you are in like robotics or rocket engineering or something like that, right? No, nobody?
Nope.
Everyone deal with basic circuits, voltage, current, resistance. You guys aware of a thing called Ohm's law?
Yes.
Oh. I don't remember.
Ohm's law says that the voltage in a circuit is equal to the product of the current that is being driven by that voltage times the resistance of that circuit. Named after Ohm because Ohm discovered it. He wasn't the first to discover it. Someone else discovered it first.
Why do I get the feeling it's Tesla?
It's not Tesla. Oh, no. Tesla's way after this stuff. At least several decades. So and then the same guy made a bunch of other discoveries too, that aren't credited to him. He does get credit for this one, probably not because he pushed for it, because he literally didn't care. Probably because someone in his family was like, "Come on, dude! Like you're doing all this great stuff. You should probably get some recognition." And so someone else probably did it on his behalf. And the reason is because we now look back and we see, and his name is Henry Cavendish, by the way. Henry Cavendish. We can now look back and see, obviously, that Henry Cavendish was severely autistic. Severely. He couldn't function on his own. He couldn't talk to women at all. If you wanted to talk to him about his scientific ideas, there were certain times where he wouldn't even look you in the face. You couldn't make eye contact with him. And so you'd have to address the room. You'd have to talk to the walls and the ceiling. And then he would listen, and then he would respond to the room. He wouldn't, and if you made eye contact, it would be over, and like he'd go, like very, very autistic. But he's also a savant. You guys, if you can't hold it together, you need to. Because if I look back there, it's really distracting. So if you're gonna either turn around or go out there, or okay, I'm being serious. All right, because now I don't even remember what I was saying. Oh yeah. So savant, you guys know what a savant is?
More or less.
Someone that is a genius, super genius, right? And there are real people like this. There are very few. There are real people like this. You guys know who Tom Cruise is? He's not very well-known actor, but Tom Cruise, very well-known actor. And before, maybe 20 years ago, when it started being all of his movies were all action movies where he just ran full speed the entire movie. Like I say the 80s and the 90s, Tom Cruise did some excellent movies, and he did some excellent acting. And there's if you ever again, you want another powerful movie, Born on the 4th of July, one of Tom Cruise's best movies. Again, not like explosion, it was not like that, but that's a great movie. He's also in a movie called Rain Man. Has anyone ever heard of a movie called Rain Man?
I haven't actually watched it.
Okay. So Dustin Hoffman is in it too, and Dustin Hoffman plays the guy Rain Man. And it's based on an actual person. Dustin Hoffman is Rain Man, and then Tom Cruise is the guy that exploits Rain Man for financial gain. But then I think it's been a while since I've seen it.
That's kind of like Ohm's law. He exploited his ideas
Kind of, but he wasn't really exploited because he just didn't care. Right?
Well, he didn't care because he didn't have.
And as you'll hear in a second, it's hard to exploit this guy because he had it pretty good. We'll just say that. Yeah. So he was a savant, and look up the real Rain Man if you ever have time, because it's incredible. You can ask they would ask this guy, they would ask him things like how much does a candy bar cost, and he'd be like $100, and then how much is a brand new house, brand new mansion, like $100. Like economics, money, that kind of stuff, no meaning to him. Couldn't understand it, couldn't function on his own. Right? He was definitely dependent on other people. And I'm talking about the Rain Man. This is a modern guy. You can watch videos about him. But they'll ask him like 2 8-digit numbers, 10-digit numbers. Multiply these two numbers, and like that, spit out the answer. Right? Savant. That's what we mean by savant. And I feel like this is even more impressive. They'd be like, okay, the year 10,940, September 16th. Don't forget leap years every 4 years. Don't forget those. What day is that going to be? And then he'd take a few seconds and be like, oh, that's going to be a Monday. 10,000 years from now, right? Like, he could do that, right? So that's the brain power that we're talking about. This guy was like that guy. And so, yeah, he didn't care. He didn't care about publishing stuff. He just loved doing science. It's what he just loved to do. When he was doing Ohm's law to make measurements of the current, he would grab the electrodes and put the current through himself. And qualitatively measure this by measuring his discomfort level. Right? That's part of what went into discovering Ohm's law for electric circuits. Yeah, the dude was legit, right? So
Build different.
so now the thing is that back then, what happened to severely autistic people? It's very sad. What did they do to severely autistic people? They stuck them in asylums, right? They stuck them in asylums that were horrible, awful places where they were horribly mistreated, usually, and they were just forgotten, right? Their families didn't want them. send him away and be forgotten. Cavendish was lucky in that he was born into one of the most wealthy families in London. Like, you're talking billionaire, at the time, billionaire status, like the richest of the rich. And so they were like, no, we love this kid, as they should. They said, we love this kid even with his disability, so we're gonna let him live his life. And then they realized shortly after, oh, there's something off here, but something special too, because this kid is brilliant. And then sure enough, they feed into his science interests, and he ends up becoming one of the greatest experimental scientists of all time, because in the late 1800s, he was able to figure this number out, to calculate it experimentally, to determine it and calculate it experimentally. And let me just tell you what the value is. This is why it took so long. This is why it took so long to figure out what the value of G was, because its value is 6.67 times 10 to the negative 11th power. Now the units are weird. Don't worry about the units, but for completeness sake, it's just used to make sure that when you calculate a force using this equation, you get it in newtons. It's newtons times meters squared over kilograms squared. Don't worry about that. You don't need to worry about that. But this, move the decimal 11 times to the left. This is a very, very tiny number. It's kind of funny because little g, for the most part, for most situations that we do, is 9.8. Big G is billions and billions and billions of times smaller than that, right? It's way smaller than that. Or billions of times smaller, I shouldn't say billions of billions. Billions of times smaller. So that's why. Newton was like, I know it's going to be small, and there's no way that with technology in the 1600s we can figure that out. And really, and this is one of the things, usually when a discovery happens in science, usually it's about to happen. And it just takes a real smart person, right? If Einstein hadn't made his discoveries of relativity, someone else would have. It would have taken a little more time. The calculus. Isaac Newton invented calculus to essentially discover what we're talking about now. Did you guys know that someone else invented calculus at the same time? His last name is Leibniz.
Didn't they have like a whole legal battle over it or something?
Well, yeah, which Newton won handily. Yeah, Newton was super rich. Newton knew people in government. Newton actually took positions in government sometimes. He put science on hold to head the Treasury Department at one point. And Newton knew a lot of people, and he had a lot of clout. And he knew this guy was inventing calculus too. And Newton was a real jerk. By all accounts, you didn't want to hang out with Newton unless you were a top-rate scientist, because he would look down at you, and he would talk bad about you, and he would talk bad about you to his friends. He was a real jerk, real piece of work. And so he made it part of his life's mission to downplay this guy's contributions. And so this guy died poor and unknown because of Isaac Newton, because Isaac Newton was such a jerk. And it's funny because when you learn calculus from Miss Fudge, the notation that you use, like these weird symbols that you might have seen here and there, and then dy over dx, this kind of stuff, this is Leibniz notation. Newton's notation for calculus was actually much more cumbersome, and so Leibniz is much better. And so shortly after Leibniz died and Newton was out of the picture, he died too, Leibniz got his credit. It's just unfortunate they didn't get it while he was alive. But anyway, why I'm saying that is when a discovery is about to happen, because that's where technology is at the time, it's bound to happen. Someone's going to discover it. There are people like Newton and Einstein and Cavendish, though, where it's like, okay, if they hadn't have been there to do it, it would have taken significantly longer, maybe decades, right? Ohm's law, like Cavendish figured it out. Ohm figured it out not too long after, right? It would have happened in that time because of the available technology and the prevalence of smart people. Cavendish figuring this out, it might have taken a few more decades before someone could have figured it out. And so I want to end today by talking about the experiment that he actually used to determine what that value is. And so it involved, we're going to look at the room that he set up, and we're going to be looking at it from the top down, okay? We're looking from the ceiling down. And by the way, you can buy, I as a physics teacher, as a physics department, we can buy the setup for this from physics supply companies to recreate this experiment in this classroom. It's several $1,000s, so it's not going to happen, but we could, theoretically. But the thing is that we wouldn't be able to do it in class. I would have to wait probably for a vacation with good weather, because once the apparatus is set up, there can be zero air currents in the room at all. Someone walking by in the hall out here would disturb the experiment. It's that sensitive. So I'd have to come in on a vacation and set it up and then leave. And I would do it with cameras because I could do that remotely. You can't be in the room because just walking into the room would influence the experiment. That's how sensitive these measurements were. That this guy was figuring out how to do in 1860 something or 1870 something, like before obviously computers, before calculators, before any of that crap. This guy figured out, and what he did, I like to think this is how the story goes, but I don't know. I like to think he went to his dad and was like, I want to do an experiment, and his dad was like, okay. He's like, I need you to buy all the lead in London, like all of it, and his dad was like, okay, and he sends his people out to buy all of the available lead in London, all of it, so that Henry Cavendish could have people create giant lead spheres, right? This is why it helps to be super rich, right? This is another reason why this might not have happened without Cavendish for quite a while, because no universities or anyone had the capital to buy as much lead as required to do this experiment, and so another reason why it might not have happened. So giant lead spheres, weighing thousands and thousands and thousands of pounds each, just giant. And then from the ceiling, he suspends this filament of wire. It's like a quartz wire where it's very known properties. You take this wire, if you twist it, you put torsion in it, right? So you guys know what a pendulum is? This is a pendulum.
Yes.
This is a conical pendulum.
Yeah.
This is a torsional pendulum. Spins up, and then it stops, and then it spins this way. And then it'll go that way until it stops, and I'm not on the video. And then it stops spinning that way, and then it starts going back the other way. And if there's no energy loss, it would do that actually forever. It would keep doing that. So just like a pendulum swings back and forth, it spins this way, and then it spins that way, right? And this quartz filament, this quartz wire filament, if you twist it by pi radians or 180 degrees, then they knew exactly how much restoring torque. Like when you let go of it, then it wants to rotate back. Well, the force that causes rotation is called a torque. And so Cavendish knew, based on the properties of this wire, that if he's suspending something, if it gets twisted, then the torque wants to twist it back, like a torsional pendulum. And so he sets up the apparatus. He continues. He puts a rod here, a lightweight rod suspended from that string from the ceiling, and puts two more lead masses, small lead masses here. And then seals up the room and leaves. And what will happen is that the gravitational force, this setup allowed him to actually create a scenario where the gravitational force between this guy and that guy, and that guy and that guy, caused this to deflect just a little bit. By an amount you can measure with a ruler? No. And he couldn't anyway because you can't go in the room. That disturbs the whole thing. This is so sensitive. So what happens, this starts to go kind of oscillate back and forth, imperceptibly almost. But Cavendish is smart, so he puts a little mirror right here. He puts a little mirror, and he opens up a little chamber here and shines a light in at night, and that light hits the mirror there and bounces off onto the wall here. And because this distance is so great, when this thing oscillates just a little bit, the light, you can see it visually moving back and forth on the wall. And by timing how long it takes to go back and forth, the period of that oscillation, he was able to, using physics that we actually learn a little bit about next year in AP Physics C, using torsional pendulums, he's able to calculate the value of G. What else goes into that? Some hardcore math that I'm not going to get into that I probably couldn't do now anyway. But what happened then, I'm going to have time for this because this is the end. Once Cavendish figures out G, you go to the place now where this happened, where this experiment was set up. It's a different house, different place, obviously. But there's a plaque that's standing there that says this is where the Earth was weighed. And they really should have said this is where the mass of the Earth was measured. Really, they should have said that. Because once you know this, you can get the mass of the Earth. You can get the mass of the Sun. Like once we know the mass of the Earth, we can get the mass of the Sun. Once we know the mass of the Sun, we can get the mass of Venus and Jupiter and all the other planets. Okay? And how do we do that? Real quick, this is fast, so watch, pay attention. I gotta go fast because we're almost out of time. Here's Evan standing on the Earth. Evan feels a gravitational force towards the Earth. Right? That gravitational force is Evan's weight, right? We know that. We've known that for years now. Force of gravity is Evan's weight, but now we have another equation, mass of Evan times G. Now we have another equation for that same force. It is big G times the mass of the Earth. Oh, Evan was a poor choice for this. Liberty. That's the Liberty. That's the Earth times the mass of Liberty. I'm sorry, Evan, but your name didn't work. Didn't work out. Over the radius, the distance is the radius of the Earth squared here, right? All right. That's not the important thing, though. What happens to Liberty's mass here? I can divide both sides by the mass of Liberty. What if I just generated an equation for it? G is big G times the mass of the Earth divided by the radius of the Earth squared. This G, Newton knew G, that's easy to measure. Drop that, time how long it takes to hit the ground, use the kinematic equations to calculate the acceleration. Radius of the Earth, the ancient Greeks figured that out, right? Or at least they figured out a way to conspire to make you all believe that the Earth is round. So, don't shuffle papers. That's another thing you need to stop doing. We knew the radius of the Earth. We knew G. We didn't know the value of big G, right? It's 200 years. So we couldn't figure out the mass of the Earth, right? This is the only equation that you can get with those two unknowns. So there's no system of equations that we can solve. We needed Cavendish to come along to find G. Once he found G, he calculated the mass of the Earth. Once we know the mass of the Earth, we can do the same thing for the Sun and the Earth to calculate the mass of the Sun. Once we know the mass of the Sun, we can do the same thing to calculate the mass of Mercury and Venus and all the other planets. Okay, so isn't that interesting? I'm sorry it went to the end, but yeah. All right. Remember our talk today. And I expect no more hysterical fits of laughter in the middle of class. If I see that, yes, Evan, please, no more hysterical fits of laughter.